In this video, we're going to learn about Euler's method, a numerical technique used to approximate solutions to first-order differential equations. We'll start by looking at the idea behind Euler's method and see where the formula that you'll need to use comes from. We'll then work through an example so that you can see how a solution is approximated step by step. Let's get started. Euler's method is a numerical technique for approximating solutions to first-order ordinary differential equations, like the one written here in this box, when an exact solution is difficult or impossible to find. Euler's method is one of the simplest numerical methods for solving a first-order ordinary differential equation. Instead of finding an exact solution, it uses the slope f of xy that's given up here in the equation to step forward from a known starting point, which we're going to call x0, y0, and that comes from the initial condition y of x0 is equal to y0, and then build an approximate solution that we're going to call x sub n, y sub n, point by point. If we look down here on our graph, we can see that our initial condition x0, y0 is what the solution is initially equal to. And then x1, y1, right here, approximates this solution. And then the next approximate solution, x2, y2, approximates this solution. Notice that x0, x1, and x2 are all equally separated by a value that we'll call h, and that's called the step size. Let's now see where the formula for Euler's method comes from. Over here on the right, we can see that the point x0, y0 is the point that we start with. That's the initial condition. And then the point x1, y1 is the first approximation. To find the approximate value for y1, we're going to use the fact that this green line is the slope of the tangent line to the solution at x0, y0. If we look back up here at the original equation, the slope is given by dy dx, and it's equal to f of xy. So we can say that f at x0, y0, which is the slope, is equal to y1 minus y0, all divided by x1 minus x0. We want to find y1, which is right here, so that's the one that we're going to solve for. If we multiply things through, we get that y1 is y0 plus our function, which is our slope, times x1 minus x0. If we look back at the graph on the left, you can see that x1 minus x0 is equal to h. So we're going to plug that in. That's right here. And that's our formula for y1. This same process is used to find y2 and all the other y's. And this leads us to the formula that we're going to use. And that formula is y sub n plus 1 is equal to y sub n plus h times f of xn, yn. I want to make one more note about step size. Using a smaller step size h generally produces a more accurate approximation. And I'll show you how that works in our example. Let's walk through an example where we're going to use Euler's method to approximate the solution of the initial value problem, dy dx is equal to 2x, and y of 1 is equal to 1, at x is equal to 1.5, using a step size h is equal to 0.1. I chose this problem to use as an example because we know the solution to this differential equation. The exact solution is y is equal to x squared. Knowing this will help us determine how accurate our approximate solution is. The formula that we're going to use is y sub n plus 1 is equal to y sub n plus our step size h times f of xn, yn. The first thing that you want to do when you're solving one of these problems is rewrite this formula in terms of the equation that we've been given. So we're going to start by writing down what f of xy is equal to. F of xy, for the example that we've been given, is just f of x, and it is the right-hand side, which is equal to 2x. It's always whatever the derivative is equal to. We can then say that f of x sub n is equal to 2xn. Let's now plug this into our formula. Our formula is y sub n plus 1 is equal to y sub n plus h times f of xn yn. Now let's plug in what f is. So we have y sub n plus 1 is equal to y sub n plus h, which in our problem is 0.1, times our function, which was 2x sub n. This gives us the formula y sub n plus 1 is equal to y sub n plus 0.2 x sub n. Writing this ahead of time just makes things a lot easier, so you don't have to go through that computation every time. Let's now look at this table down here on the left and fill in what we need to find. You're always going to start with n is equal to 0, and we can find x0 and y0 by looking back up here at our initial condition. Our initial condition tells us that x0 is equal to 1 and y0 is equal to 1. So we can put that into our chart. We'll fill out what the exact numbers are when we get done with our problem. We want to find an approximate solution at x is equal to 1.5, and our step size is 0.1. So x is going to be 1.1, 1.2, and then 1.3, 1.4, and 1.5. We're just adding our step size onto each value of x. We started with n is equal to 0, so then n is going to be 1, 2, 3, 4, and 5. Now we have to start computing what our values of y are. Let's start by saying that y0 is equal to 1, and let's make a note that x0 is also equal to 1, because we're going to need that. y1, looking over here up at the right at our formula, is going to be y0 plus 0.2 times x0. So this is 1 plus 0.2 times 1, and this gives us a value of 1.2. Let's go back up to our table and let's put that in. y1 is equal to 1.2. Now let's compute y2. It is equal to y1 plus 0.2 x1. y1 we just found was 1.2, and then we add 0.2. x1 is up in our table, and it is equal to 1.1. And this gives us a value of 1.42. And let's put that up here into our chart. Now we're going to compute y3. It is equal to y2 plus 0.2 times x2. y2 was 1.42. And then we multiply 0.2 times x2, which is 1.2. And we get a value of 1.66. Let's now compute y4. I'm not going to write down the formula because I think we already know what the pattern's going to be. y3 is our previous solution, 1.66, and then we add on 0.2 times our next x value, which is 1.3, and we get an answer of 1.92. Let's do it once more. y5 is equal to 1.92 plus 0.2 times 1.4, and this gives us a value of 2.2. Let's now put these values back up into our chart. We have 1.66, 1.92, and 2.2. We can now write down what our approximate solution is. We can say y at 1.5 is approximately 2.2. Let's now go back up to our table and put in the exact value, and then we can see how accurate the solution is. Our exact solution was y is equal to x squared. So when n is equal to 0, our exact solution is 1 squared, which is 1, and then we have 1.1 squared, which is 1.21, and then we get the rest of the values. We're just squaring what xn is. Going back to our approximate solution, we can compare this to our exact solution, which is equal to 2.25. So we can say that the absolute error is going to be our exact solution, 2.25, minus our approximate solution. And we have an absolute error of 0.05. And let's make a note, this is when our step size is 0.1. If we would have used a smaller step size, say h is equal to 0.01, we would have found that y at 1.5 is approximately 2.245. You have to do lots and lots of computations to get to this answer. The absolute error for this one would be 2.25 minus 2.245, which is equal to 0.005. And let's just mark this is h is equal to 0.01. You can see from this that if you use a smaller step size, your error is going to be much smaller. And that's it. You now know how to use Euler's method to construct an approximate solution and how the step size h affects the accuracy of the solution. You should be all set now to work through some practice problems on your own. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.